So I'll talk about anisotropic distributions, so a class of probability distributions on manifolds, and what I call diffusion PCA, and then evolution equations that are connected to this construction. Okay, so the overall setting here is performing statistics on data that lies in a geometric space. So this could, for example, be statistics of shape. It could be, that's a corpus callosum. You see there, it could be statistics of on the diffeomorphism group. At least what I will talk about here is a finite dimensional setting, but you can imagine that. Here's a low dimensional case, which is just for visualization, but you will see this picture again. So the data here, so the data really points in the geometric space, and you see an example of some sample data here, and then I've estimated a mean, and this ellipsis corresponds to the covariance matrix of the data. So you can see there's anisotropy in this direction, and this anisotropy is a major point of the talk. Okay, so these examples, they all live in nonlinear spaces, but anyway, we would like to be able to look at what is variation. So here you see the variation along a geodesic in the corpus callosum shape space. Or we would like to produce a picture like what you see up there, which is a plot corresponding to the first two principal components of the data. So for statistics on manifolds, the Fresh mean is usually the starting point. It is minimized of the square distance to the data, and then so that's a zero-dimensional descriptor. Then if you go a little bit further, then like examples of some constructions are generalizations of principal component analysis. And there are a number of these, and I've drawn some of them here, and they seem to sort of exemplify the difficulties of doing statistics in geometric spaces. So that's why they're interesting to study, I mean, for that purpose, but also for applications. So just briefly to go over some examples. Principal geodesic analysis uses the tangent space of the mean, at least in some formulations, and does PCA in the tangent space. So that's a linear space that sits at the mean, but the manifold is of course nonlinear. There's a geodesic PCA which fits geodesics to the data, so these are one-dimensional subspaces. And then there are some other ways of constructing low-dimensional subspaces corresponding to the linear subspaces in Euclidean principal component analysis. I talked about one called HCA at the last DSI, and Xavier is talking about barycentric subspaces in the next talk. So here I will, so these examples all had a construction of a subspace as a general tool. Here I will take a different approach. So I will, what I will do is define a family of probability distributions, and these will mimic Gaussian distributions in Euclidean space. And then I'll fit these to data with maximum likelihood, for example. And this will sort of, this is a different approach than using, than finding a subspace, and it corresponds to what in Euclidean space is called probabilistic PCA. But it's just a formulation of PCA which centers around finding a Gaussian and fit a Gaussian to data. Okay, so now the problem is, what is a Gaussian and an anisotropic or general family of Gaussian distributions in a geometric space? So one way to approach it will be to look at what is like if you take an isotropic normal distribution in Euclidean space, you can define it by its density function, but you can also look at it as a transition density of a diffusion process. And so that works in Euclidean space, and it actually also works on the manifold. So on the manifold, you can you can define the Brownian motion. You can start a Brownian motion at a point, let it run for some time, and then stop it. And the transition density is then like a way to talk about a normal distribution. You could also look at the solution to the heat equation. It gives you something similar. So a point about these two ways of doing it is that they are infinitesimal. So the stochastic process works infinitesimally, and this PD is also defined purely from the infinitesimal structure of the manifold. So this is different than if you use the density function in Euclidean space, where you have the difference between two vectors. So it's easier to work with things that are infinitesimal than global notions like difference between two vectors. So we'll see this again. Okay, so this was the isotropic situation, and in a moment I will make this work for in an anisotropic situation. But if we just assume that this is possible, and it will work like with the diffusion process in the same sense, but the technical details will be in a moment. Then, if it's possible, then we can define a map that I call diff, and diff is for diffusion, but this is a map that generates these probability distributions, and it's a map from the frame bundle. So the frame bundle consists of points on the manifolds and bases at the tangent space of the point. And you can think of this as, if you specify a normal distribution in Euclidean space, you specify the mean and the covariance matrix. These points in the frame bundle will define a mean, sort of a mean, and a square root covariance matrix. And then giving those, this map gives you maps into the probability distributions, and if you have some kind of base measure, then you have a density. So this map is just a way to generate something that looks like a normal distribution. And the image of the map will then be the set of normal distributions, and we have a density function for each of these parameters. So if we have some data in the slide called yi, then we can write up the likelihood function, and then we can maximize that. So then we find the maximum likelihood, which is then a point in the frame bundle. It's a point corresponding to the mean and a point corresponding to the square root covariance matrix that makes the data that is as likely as possible with the given data. And then this diffusion PCA procedure is built upon this notion. And if you know the probabilistic PCA in Euclidean space, it is exactly the same approach that you fit Gaussian distributions to data by maximum likelihood. Okay, so if we can define this map, then everything is fine. Okay, so let's go about that. So if you again take the Euclidean example as a starting point, then I talked about the isotropic normal distributions before. If you go to the anisotropic case, then you have a density, and when you value that, then you have an inverse covariance matrix in the middle here. So that you can also look at as the transition probability of a diffusion process. And you can actually also talk about, or you can actually find out what is the most probable. So it's a stochastic process, so there are a number of sample paths radiating out from the starting point and hitting each data point, and then you can talk about what is the most probable way of getting that, what is the most probable among these sample paths, and that would just be the straight line. Okay, so if we can do the same trick on the manifold, define something which is anisotropic, which radiates out as a stochastic process, then we could also look at what is the most probable path again, and then we would get something like what you see up there. And one could then ask, do they correspond to the straight line in some way? Do they correspond to geodesics, for example? Okay, so the problem with this approach is if we are in an anisotropic situation, and if we did it in Euclidean space, we would have the stochastic process would have a stochastic generator, or its square root, the diffusion field, and it would be stationary in space. And then if we do that, try to do the same on the manifold, we get into problem, because if we try to mimic this stationarity, then what would be most natural to do would say that it should be parallel transported along each of these stochastic sample paths. But if you start with some anisotropic generator here, and you parallel transport it along one path or another path, then you get different answers at the same point. So this is a holonomy of the manifold that gives the difference between the parallel transport, and that means that this stationarity doesn't really work as long as you have something which is anisotropic. In the isotropic case, it doesn't matter because you just rotate the same matrix. Okay, so a way to then go about this is to use a process called, or construction called stochastic development. It's also used in the Ellsworthy-Madhivan construction of Brownian motion. And it works in the following way. So we have, the manifold is n-dimensional, and we have Rn here. And then we can run a diffusion process in Rn, so you can just think of that as a standard Brownian motion. Then for each sample path in Rn, we make a map called phi to the frame bundle of the manifold. And the only thing that we need in order to start this process or map the sample path to the frame bundle is to specify a starting point. So there's a starting point on the manifold, and then also a starting frame. So given a point and a frame, then you can map a sample path in Rn, so sample path on the manifold, and then you can, so remember the frame bundle was points and bases. So having such a path, then you can throw away the bases, and then you get a path on the manifold. Okay, so here you have a stochastic process. Then for each sample path, you map it like this. You throw away the frames, and then you get a number of sample paths on the manifold, and then you can take the transition probability of that, and that will give you the density that we are looking for. So I call this process in Rn for the driving process. It's here in these slides I denoted xt, so it's a standard Rn value Brownian motion. Then we have a process on the manifold, which is the one we're interested in. I call it yt, and I also denoted the target process. And then we have a process in the frame bundle, which I denote or call ut, and it's a subelliptic diffusion in the frame bundle. Okay, so the frame bundle is pairs of points on the manifold and frames of the tangent spaces. And it has a nice and quite important splitting. So if you look at the frame bundle and take the tangent bundle of the frame bundle, that's TFM, then it splits into the horizontal and the vertical space. So the vertical space is what you get if you fix the base point and twist the frame. And the horizontal space is what you get if you move on the manifold and parallel transport the frame along the same path. And so we have the usual projection map from Fm to M, and then you can take the push forward of that. And actually, if you fix a frame here, then you can also go the other way. So if you have a movement on the manifold, then you can get the corresponding horizontal movement in the frame bundle. And this is important because it gives you n globally defined horizontal vector fields in the frame bundle. They are called HI here. They just correspond to movement on the manifold and parallel transport in the same direction. So now if we have a Brownian motion or any semi-martingale in Euclidean space, then we can multiply them on the horizontal vector field. This is what takes place here. And that gives us the process in the frame bundle. And then we can throw away the frames by projecting down, and then we get the process on the manifold. So it's kind of a natural construction. You can also look at or visualize the process in the frame bundle like this. You have all the sample paths radiating out. They each carry with them a frame. And the frame, every time they take a new step, then they do that with respect to the frame they have at the point, and then they carry the frame with them by parallel transport. Okay, so running these processes, stopping them at a certain time, and taking the transition probability, we get this family of probability distributions. And just to give you some examples here, I sampled some paths on this field. This is the same picture as you saw in the first slide. And then I optimize for the mean, which is a green point. And this ellipsoid shows not the frame, but the frame multiplied on its transpose. So this is sort of the anisotropic you see in a standard covariance matrix. This is a different example from, these are the corpus callosum data. I represent them with landmarks, and then in the same way as before, I find the mean with this construction. Okay, so everything here is generated by processes. So then one can ask, what are the most probable ways of reaching given data points? So in a sense, if you observe a data point, it's coming from, under this model, it's coming from a sequence of stochastic perturbations of the mean. And then you're looking for what is the most likely sequence of events that brought you to a given place. So usually when you talk about most probable paths on manifolds, it's defined via the on-cycle-mass loop functional. And you see it here, it has, if the curve is called sigma, then this term here is just the usual squared derivative, the norm of the derivative of the velocity. But then there's an added term, which is 1/12 times the scalar curvature of the manifold. And this, so actually, so it's a little bit difficult to talk about most probable paths because sample paths are almost surely nowhere differentiable. So the way the unsaccharomyces functional is defined is by taking a small tube around the path, looking at the probability of sample paths staying in this tube, and then letting the tube go to 0, the diameter of the tube. And so, so maybe you can imagine when you take this tube and take the limit as it goes to 0, then the curvature term appears here. So basically doing this is taking a small tube on the manifold, and then you get this, this functional. So this is some way of doing it for the target process. You could also imagine just taking the tube and moving it to the driving process, to the Euclidean process. And there's a one-to-one correspondence between the sample path up here and the sample path up here. So you can define the tube in whichever space you like. And of course, this is a Euclidean space, so the scalar curvature is 0, and then this term vanishes. So left you are with the usual geodesic, or usual length, what call it, norm of the velocity of a curve. So actually, if you do this definition is just capturing. You take your condition of a path of hitting a point on a manifold, but you take the probability for the driving process in Rn. Then the most probable path with this definition maps to geodesics, actually in a sub-Riemannian metric on the frame bundle. I'll define this in a minute. But it's interesting to look at the isotropic case, so the case where the frame is orthonormal to begin with, because then this sub-Riemannian metric just corresponds to the usual metric on the manifold, and then we get geodesics back. So in the isotropic case, these most probable paths for the driving process correspond to geodesics. So it's different than the unsaccharomyces functional still. And then one could, at least with some hand waves, say if instead of, when we do this maximum likelihood fits of the data, instead of looking at the actual likelihood, if we instead approximate that by the probability of the most probable path, so actually the log probability of that, and optimize that, then we get the Fresnel mean back. So, but that's in the isotropic case. Okay, so here you see 3 examples of a process starting at the North Pole, and then I condition on hitting a point on the southern hemisphere. And this is the isotropic case, and here you see increasing anisotropy. So this is, so in the isotropic case, so this is the most probable path, this is just a regular geodesic. In the isotropic case, they correspond, and then you see them deviating more and more from the geodesic. These vectors here correspond to the frame being parallel transported along the path. So this gives us sort of a wider set of curves, and they come from this anisotropy of the process. Okay, so the sub-Riemannian geometry on the frame bundle that these are geodesics with respect to is kind of natural. So every time we have a frame, the frame is a basis, so it's a map from Rn into the tangent space of the point on which it is a frame. And it's invertible, so we can, if we have 2 vectors in the tangent space, we can take the inverse of this map. This is what you see here. And then if you take the Rn inner product, that gives you a new product. And this inner product exactly corresponds to when you write up the density for an anisotropic Euclidean Gaussian, then you have the minus the inverse covariance matrix in between. This is exactly what goes on here. Okay, so then the most probable paths you can find as minimizing the norm of the norm coming from the inner product of paths conditioned on that these frames should be parallel transported. But you could write the same problem as looking for extremal curves in the frame bundle with a sub-Riemannian metric, which is defined exactly from this inner product. And it's sub-Riemannian because you are only allowed to move in the horizontal space, and this metric is degenerate on the vertical space. Okay, so these are sub-Riemannian geodesics, so we can write up the Hamilton-Jacobi equations, and we can do that in coordinates, and then we get the expression, the equations that the expressions for the curves you saw on the sphere a little back. But these are general; they are not limited to the sphere. That general expressions, and you can actually see here is gamma, which is so the crystal Feld symbols appear here. Okay, so you can also do this for LDDMM. Landmark LDDMM is a finite dimensional manifold, and here you see two examples. This is the last slide. So this is geodesics between a geodesic between 2 points to 2 other points in the isotropic situation, and here's anisotropic in the horizontal direction, and here it's in the vertical direction. So that gives different pictures of what a geodesic is. Okay, and let me stop here.
So we have time for question. And the idea is to keep a few minutes for some questions. So, no question in the audience? Yeah?
So maybe a connection to the situation on statistical manifolds where you basically have a Riemannian metric and you have a connection which are separate, if you like. And here similarly it appears that you have the covariance matrix, which is transport gives you a Riemannian metric, maybe, and you also have the parallel transport that comes from the original Riemann structure on your manifold. Is that something?
Yes, certainly. So as soon as you have the covariance matrix, then the connection is like the vehicle here. There's no direct. Usually, you would, if you have a Riemannian metric, you would use the Levi-Civita connection and get the parallel transport from that. But you can just start with a connection, and then transport everything is defined from that connection. So you're completely right. You can just go from the connection and use that.
Okay, other questions? So yeah, I have one question, which is if now you want to use this type of estimation, how do you think you will be able? Do you think you will be able to estimate the subspaces or the covariance matrix from the or subcovariant subspace from there? Is it something that you think is achievable, or is it?
So I think so. When the examples I showed you here, then I instead of so I used the probability of the most probable path as a placeholder for the transition probability, and then it's feasible. Then it's very much like optimizing with geodesics, like for the Fréchet mean. But of course, that's a rough approximation because the transition probability is not given by that. And then I think otherwise, probably the feasible way to do it would be to sample. So some kind of sampling scheme to evaluate and perhaps on a Lie group, it's more. You have some structure to work with. Otherwise, it's pretty heavy computationally to sample a lot of points. But I mean, I think it's feasible. Maybe not fast.
Okay, thanks the speaker again.